Good evening. We are the founding members of Solarlene Green 3D Printing. The problem we are trying to solve is it possible to 3D print an object mainly from sunlight and air? Here is our proposed process schematic. As you can see, we are taking CO2 from the atmosphere and methane to produce ethylene and polyethylene to ultimately 3D print objects just by using solar power. The first unit we are going to examine is the carbon capture and the methane feeds. We're going to utilize direct air capture to produce pure compressed CO2 from atmospheric air, water, and renewable energy. We're going to use a solid sorbent system that requires 80 to 120 degrees Celsius to release the bound CO2 in pure gas form. The energy from the photovoltaic array can easily provide the heat necessary to carry out this process. We're going to obtain our methane from a clean source, such as biomass gasification, to use as a feedstock.
The electrochemical cell shown in the schematics suggests two possible mechanisms in order to produce ethylene from greenhouse gases, namely carbon dioxide and methane. Wang's article on green ethylene production suggests two mechanisms exploring the integration of cathodic carbon dioxide reduction with anodic methane dehydrogenation for parallel ethylene production using three-phase electrochemistry. The average suggested efficiency of the two fell somewhere between as high as 70 and 80% with temperature and environmental factors considered. In summary, the harnessed CO2 and methane could be fed to the electrochemical cell in order to produce ethylene.
The final part we're going to talk about is the polymerization and extrusion. The general reaction is shown here, ethylene to polyethylene. And we can use different reactor types, such as CSCRs, continuous stirred tank reactors, or loop reactors if we're using a slurry or solution process, or a fixed bed reactor if we're using a gas phase process. Often combinations of both are used. The general reactor conditions would be 10 to 80 atmosphere as pressure and 80 to 180 degrees Celsius as temperature. We'd need an initiator if we're using low density polyethylene as product, or a catalyst such as the Ziegler-Natta or metallocene catalyst for high density polyethylene, which is more ideal for 3D printing. The ideal extrusion temperatures would be 200 to 260 degrees Celsius and a bed of 100 to 130 degrees Celsius to have a good 3D print. So now the technological status. We made our calculations using a basis of 1 kilogram of polyethylene product per hour, which is similar to 3D printing results. Assuming a 20% efficiency, we found a total required solar panel area of 162.5 meters squared. You can see the details below. The cost would be $13 per kilogram hour of polyethylene, and the current market price of polyethylene is 98 cents per kilogram. You can see a vast difference, but hopefully those prices can go down with technology.
Taking a look at the advantages and risks here, two of the largest advantages here is that we're utilizing two of the most highly emitted greenhouse gases while creating a centralized manufacturing system. And additionally, the HDPE filament is cheap and versatile as well as recyclable, which makes it good for materials. Despite the exciting potential, a lot of the technology and research proposed is still novel and requires large amounts of capital investment and time to better understand additional implications and risks. Thanks for listening.